So when working with the speed of light, there are generally two equations that we use. The first one we'll use in this equation, or this problem, involves wavelength and frequency. And so that is the equation often called the wave equation, that v is equal to f times lambda. And if you're told that the problem involves light, then you should assume that the speed of light is 3 times 10 to the 8 meters per second. That's our value for speed of light in a vacuum. And you should use that unless you're told something specific about the material that would cause you to think it to be significantly otherwise. So remember, c is the symbol we use for the speed of light, but it is just a velocity, a speed. So it's just v in a vacuum. All right, so usually when these problems come up, it involves some converting of units, because a light tends to have a very small wavelength. Visible light is in the nanometer range, and so you can see here that's what this stands for, 556 nanometers, nm. And so we need to convert that value. So let's do that first. 556 nanometers, and then we'll set up a proportion here that there are 10 to the negative 9 meters versus 1 nanometer. Make sure that your units cancel out. And then, so that tells us just to multiply 5.56 times 10 to the negative 9. And so our wavelength in standard units is 5.56 times 10 to the negative 7. And we are looking for the frequency, so I'm going to go ahead and rearrange the equation up here so that the f is by itself. So f would be the speed of the wave divided by the wavelength of the wave. And so we'd put in our speed of light, 3 times 10 to the 8th meters per second, divided by our wavelength, which is 5.56 times 10 to the negative 7th. And our meters would cancel out, leaving us with per seconds. But we don't usually label that answer as per seconds. We usually label it with hertz, Hz. So when we plug this into our calculator, we're going to get a very big number because we're dividing by a very small number. And our answer comes out to be 5.40 times 10 to the 14th hertz. That's the frequency of yellow light. The other formula that we often use when dealing with light, the speed of light, is just our old friend here, that the distance something travels is equal to its speed times time. Okay, that's what we use if something moves with a constant speed, which light does within a particular material. So again, this is a case where we would use the speed of light as 3 times 10 to the 8th. But there's a little trick to this. So let's sketch this out so we make sure we understand what's going on, not just grab values and plug them in. The distance to the moon can be found with the help of mirrors. So we send a pulse of light from the Earth. Okay, so here's the Earth. So the light is going to go here. It's going to hit the moon. And then the pulse of light returns back to Earth. And then that's the time that we measure. So the time to go there and back is this 2.562. This is the full round trip. So what we need, though, because we're looking for the distance just to the moon, not all the way back again, what we need to do is to take this time and divide it in half so that we only have the amount of time to go one way. So if we divide this in half, we get 1.281, and that's what we're going to use in our formula then. So to find our distance, we would take the speed of light, which is 3 times 10 to the 8th meters per second, and we would multiply it by this time, 1.281 seconds. Our seconds cancels out. We end up with an answer in meters. And we expect a big number here because we are measuring the distance all the way to the moon from the Earth. 3.84 times 10 to the 8th meters.